Alrighty, here we are on 3.3, day 2, function notation. So we spent a lot of time introducing function notation, section 3.3. So remember that function notation is just another way to find a y. It has some uses, especially in graphing situations where we could label them differently. Like you would have f of x be one graph and g of x be a different graph. So then you can tell which one's which instead of just having y equals and y equals, and then it'd be a little confusing. So find the value of x so the function has the given value. So if you remember at the end of the lesson yesterday, or whatever that was, it says, if it tells you the value of the function, it tells you f of x is 21, then I make sure I plug that in here. So here's the problem. F of x equals 6x plus 9. It tells me the value of the function is 21, so I put 21 in place of f of x. Then it's just a matter of working backwards to solve the equation. 21 minus 9 is 12. Divide by 6, I get 2 for x. Okay, not too bad. I'm not going to do the next one here because I want to talk about graphing a little bit more. So if I have a function, so again I'll rewrite this. This is number 6, f of x equals 3x minus 2. The way that we graph these functions right now is we just make a chart, and you can pick any values you want for x and plug them in. I'm going to go -1, 0, and 2. Like I said, you can pick anything you want. Try to keep them on the smaller side, but when you plug them in, you take these values for x and substitute them into your function. So f of -1 equals 3 times -1 minus 2. 3 times -1 is -3. That's -5. So when I plug in -1, I get -5 back out. I'm telling you right now, be careful with your signs. That's the biggest problem kids run into in these problems, is messing up signs. Okay? So next one says plug in 0. So I'm going to plug in 0. 3 times 0 is 0. 0 minus 2 is -2. All right. Once you get rolling on some of these, they do go pretty quick. And the last one here, plug in 2. 3 times 2 is 6. 6 minus 2 is 4. Now, you graph those values. I put -1 for my first one, I got -5. When I plugged in 0, I got 2, -2. When I plugged in 2, I got 4. That's a terrible line. When you're doing this, you'll be doing it on a computer. It's one of the reasons I love big ideas. Instead of looking at your messy handwriting, your points will line up. If they don't line up, you've done something wrong. Go back and fix it. I can't tell you exactly which one's wrong. It could be any one of the 3. More points makes you more accurate. So you don't have to do just 3 here. You could do 4, you could do 5. The more points you substitute and plug in, the more accurate your line will be. So the less points you do, the less accurate you'll be. So that's something to keep in mind. And like I said, you guys won't be drawing this freehand on your assignments, so there's no excuse for your points not lining up. And I do want to take one quick mention about something like number 8. So this says h of x equals -3/4 x minus 1. So if there is a fraction coefficient here, I'm just going to straight up tell you the best numbers to plug in if you want to avoid fractions. If you don't mind fractions, you can plug in anything you want. But I know most of you hate fractions. And I know this. I'm just going to show you real quick. If I plug in 1, that's -3/4. That's -3 3/4. So when I plug in 1, I get -3 3/4. That's going to be tough to graph. If you want to avoid fractions, the numbers you plug in should be multiples of the denominator. Write that down. Multiples of the denominator. So if I plug in 4, now, and you may need a calculator for some of these, when I multiply this together, I'm going to get -3. Add that together, I get -4. So when I plug in 4, I get -4. That's easy to graph. So if there's a fraction coefficient, you should choose multiples of the denominator. So here I would do 4, 0 is always a great one, -4, 8. Those would be the numbers to plug in on a problem like this. All right, and talk about some word problems. So this says this is a graph of a miles of a helicopter. So first off, you need to be able to interpret and read these graphs. This is its first flight. So I'll draw this a little bit bigger for you. So this is this graph right here. How far is this flight? Okay, where did they start? How far did they travel? Well, I can look here. This is my distance. They started 300 miles away and they traveled, and now they're 0 miles away. So they've traveled 300 miles. Okay, that's what this graph is telling me. How long did the flight take? Well, when they're 0 miles away, 3 hours. So I can look at this graph and say they did 300 miles in 3 hours. So I have some information here. So this word problem here, I know you can't read it, says on flight 2, travels 50 miles farther and increases its speed by 25 miles per hour. So it gives me this function here. 50 miles farther, so now it's 350 is flight 2. And it goes 25 miles an hour faster, so it's going 125. And the question is, which flight takes less time? Okay. So you could do some guessing and checking here, but that's kind of ridiculous. So think about this here. When you are flying, these over here, going back to section 3.2, these are my outputs. These are my inputs. So I input a time and I output a distance. So at time 1, they are 200 miles away. So in 1 hour of flight, they're now 200 miles away. In 2 hours of flight, I can read this graph, they're now 100 miles away. So the output is just going and reading over, finding the value. So this is 1, 200. Input, output, 1 hour of flight, 200 miles away. This point right here is 100. 2 hours of flight, 100 miles away. So you can read this graph here. This, 3 hours of flight, 0 miles away. They've arrived. I can keep this in mind because when they have arrived at their destination, they're now 0 miles away. Well, remember, this is input, output. Same thing here. This goes back to everything we've been talking about, is my independent variable. That is my independent variable, that is my input. This is my dependent variable, that is my output. So the way you look at a function or an equation is the same information that's in the graph. So now if I want to know how long it takes them to fly in this scenario and arrive at the destination, what is the mileage? How far away are they at the end of the flight? So think about that for a second. How far away are you at the end of the flight? 0. You are 0 miles away at the end of the flight. So now I can plug 0 in for my output and solve the equation, just like we did on that previous section. Add, so I would subtract 350 to get negative 125x, divide everything by negative 125, punch that into your calculator. 350 divided by 125 is going to be, what is it? It's like 3.75, I think. 3.6. What do we got here? We've got 350 divided by negative 350 divided by negative 125. 2.8, sorry. So we get 2.8. So what does that mean? What is that? X is my hours, X is my input. How long did this flight take? 2.8 hours. Which flight takes less time? Flight 2. The overall thing I want you to understand here is how equations and graphs are giving you the same type of information once you know how to read them. All right. What if that was the equation for the second flight? Well, what is this telling me? 250 miles away and they're only going 75. So we can do the same thing here. Which flight takes less time? So same concept when they are arriving. How far away are they when they're arriving? 0 miles. Subtract 250. Divide by 75. 450, 250. Wrong button. 3 1/3. So that's 3 1/3. So this is the longest situation. Okay, so this one would be longer than either of the other two. All right. So again, understand how functions and graphs relate to each other. They're giving you pieces of information, looking and reading the graph with its input and output. And that's it. Put that back up. That's the end of section 3.3, day 2. Good luck. Ask questions.